So I have the difficult task of keeping you all awake. I hope you had a good lunch. I'll try and do that, and you can tell me if I did it well. So why is this coverage reloaded? Because in a recent verification futures talk, I talked about a coverage solution that Onespin has. I didn't think I had enough time to do justice to the technical side of the story. And I said to Mike, if you give me half an hour in this conference, I can try and do that. So everybody who's here, who's ever done verification, would probably relate to this loop, which is starting from requirements, you go through a plan, you build your test bench, then you run the test bench, you find failures, you want to debug them. And then the internal question, as Vince also pointed out in the morning, coverage, sign off, or just the date in hand, and we say we'll ship it off anyways. So this talk is about using a tool in an assisted way to guide you in your sign-off process. So I'm going to talk about this. If you don't measure, you don't know. I think Harry Foster said this, I think, some time ago. And I think everybody would it's not rocket science, you'll all agree. Some sort of measurement is required. Some of the challenges that actually face all the verification engineers is, when am I done? And when am I done is a question that actually can be answered if you answer some of the other ones. For example, have I written enough stimuli to cover all requirements? What part of the design has been exercised by my assertions and covers? So I'm assuming in this context you're using formal verification, but some of these or all of these actually are relevant to other forms of verification too. Have I written good quality checks? What does quality mean? Which parts of the design has been checked by my checkers? And are all specified functions implemented? Or have I forgot to implement certain features or functions? And are all specified functions verified? So the top 4 questions are addressed by a tool that we have, which is called Quantify. And it is meant to quantify the effect of having had a verification test bench. The last 2 questions are addressed by our completeness solution, which is sold as gap-free. And it is about finding gaps in your specification. So whereas gap-free is more on the lines of validation, you can think of Quantify as more as problem of solving verification at some sort of abstraction level. That's the difference. So in today's talk, I'll talk more about how you use Quantify to attain the information for sign-off. So coverage and bugs. I have been in EDA for about 8 months or so. I've been a user of formal verification tools for many years, and we talked about these things in this room, in this conference and others. And we always questioned why bug hunting and collection of bugs, which is an anecdotal exercise, should be seen any different from the coverage exercise, where coverage could be an analytical way of collecting data and bugs are usually anecdotal. Both are actually equally important, and the way we see this in Onespin is there's 2 sides to the same coin. I like to think of it as a marriage made in heaven. For some reason, had been in divorce for many years, so we're trying to bring the 2 back. So 100% coverage with bugs in design is unacceptable. I think we've all been there where we have 100% code coverage, functional coverage, and for many different reasons, we could still have bugs. The thing to note here is, okay, we've got to collect some metrics. We've got to tie them to the bugs that we are finding. We need to assess the quality of the test bench and answer the questions. But what is the overhead of doing all of this? Is it the same as your actual verification task? Is it more? Is it a small delta? So we believe that extracting coverage should be quick. The process itself should not be a long-winded process. It should be easy to get the data out, and the report should be meaningful. So I'll try and persuade you to think in the direction that Quantify offers you that solution. So where quantity and quality meet is in a metric-driven sense, when you actually have a single metric which gives you an indicator of the quality of your verification. So what happens if you were using Quantify is you take it as an input, a hardware design and a formal test bench. You run your proofs, you have some bounded proofs, you have some failed proofs, you have some exhaustive proofs, you have your constraints, and you run a single command and it produces a metric-driven report linked to your design browser as an output. And it provides 2 types of information. One is on the structural coverage and the other is on functional coverage. The structural coverage is a way to figure out whether your design was well formed and whether you were able to exercise all the areas of the design by your checkers. Even if you don't have any checkers, in this case assertions, you could still find out artifacts about your design. Functional coverage comes to you because you have requirements specified as assertions. And we are then able to take the functional coverage information and the structural coverage information and then build a coverage model, and we produce a single report and a single metric to give you the overall progress indicator. So I'll show you in an example. I also believe that coverage and this verification loop I showed you is an iterative loop, and actually collection of coverage and signing off using coverage should start from the first hour of writing the design. And I'm hoping that in the example I'm going to show you, you'll find it, that it's possible to do it that way. So we believe that the designer bring up phase of the activity, when you're writing up your design, you have or may not have any complete set of requirements. You could still run Quantify, and you can start collecting information on reachability, on dead code, redundant code. So if you're a low power company who wants to make sure you haven't got wasted area in your design, no need to wait until your synthesis part. We could find you redundant code on day one. And where quality and quantity both matter is when you're truly assessing the quality of your verification. And to keep it simple, I think of them as three different things: missing checks, over constraints, and missed bugs, or when you find them. So if you can do all these three things in a single view, in a single frame of window, then that would be quite great. So what we do is we actually, so the way to solve this problem properly, you need to be able to distinguish how to assess the results, because they're all kind of different in some ways. So we have about 9 different categories in which we split the results. To keep it simple, I have 6 categories here, and I'll show you the other 3 on the next slides. What we are really saying here is, give me the controllability information, meaning am I able to make an assessment that my design code is reachable? Is it over constrained, or is it just dead, regardless of the constraints? I can get this information. However, in the case of Quantify, the way we do this is we rely on your assertions. So when I say reached by an assertion, it means if you don't have an assertion, you don't get reachable information. However, we do have in the tool a feature which gives you reachability analysis without having to have an assertion. But in the context of the Quantify solution in the metric-driven verification view, you do need checkers, otherwise you don't get the coverage. If you do accidentally write some over constraints, then you can find this by actually looking at your dashboard view, and it will tell you that this bit of the design is unreachable and is unobservable. And you can have dead code regardless of your constraints, so we are able to split it out and say, this is truly dead regardless of the constraints. In the observability model, we want to make an assessment on what happened when these lines of code were actually activated in the controllability phase. Did they actually do anything sensible? Okay, it was possible to reach them, but do they produce the desired effect on executing them? And it is this runtime behavior, if you like, is actually obtained by running an observability analysis. So if you can actually observe each and every line of your design with respect to assertions, then you say the whole design is covered. If a specific line is not reached and not observed, then we say it's uncovered. But it's possible that you may be wiggling a line, it may be getting activated, but it actually does not do sensible stuff, meaning it doesn't actually do anything meaningful with respect to the assertions. So you could still be lacking the observability effect. So that if that happens, then we say it's unobserved. So you have to be alarmed if you actually get anything other than light green. So if you're over constrained, or you're dead, or you're uncovered, or you're unobserved. If you're in the green area, you're good. So what happens is we run Quantify, and it produces a dashboard view. It has 4 different components. I've only shown 3 here. Didn't have much space. I'll show you in the next few slides. What's happening in the top part of the dashboard is it's a single metric. At the very top, it actually is shown as 80% of the design is covered, and it shows that the assertions were exercised here at the bottom half, and in the middle it tells you if you wanted to exclude certain code because it was verification code, or if it was just redundant code, or you could manually control the waiver part of it. It also tells you whether you had a witness passed, what was the radius, tells you which branches were covered. Now, if you are interested in finding out what happens, why am I only getting 80% coverage, then you can actually just open up the design browser. And what happens then is you start getting this information in a color-coded format that makes it really easy to figure out what's going on. So the top part, which is the green, is covered. This bit is over-constrained. This is dead. And this bit is uncovered. So now you can look at a certain code in the design and can make sense out of it as to why it is uncovered or unobserved or dead. So let me show you this on my favorite example, and quite a few people in the room who know me from FIFO seem to have the same reputation in Onespin now. So what I'll show you in this example is a test design. So we have this design which is a circular buffer, so reset and clock pins. It has a write and a read on a handshake, takes data in, reads data out, read and write pointers, an internal data array, and empty and full flags. So what we really wanted for this device is to keep the data correctly ordered, not drop it, and can't reorder it, and can't duplicate it. So at a very high level, if I was building a serialized device, I would expect that device to have this behavior. It so happens that this is a FIFO here. Now, I'm not saying you have a proper verification planner. It would be good if you had one, and you can write this systematically in a planner of your choice, and you can still start the verification. But even if you didn't have any of that and you were using a good old directed test bench to actually start testing the device, you could use formal instead, and you can get better coverage because it's exhaustive. But equally, now you want the true sign-off information. So what we'll do is, even before we write any test bench, this is the fourth part of the dashboard, we'll just run the coverage tool, okay? And it confirms that actually the whole design is uncovered. It actually could have had dead code. In this example, it didn't have dead code. If it did have dead code, it will mark it as black. So because we haven't written anything, there's nothing to cover against. And it shows you the design browser view. Everything is red. In the morning, you're a verification manager. Walk through your engineer's desks, have a quick glance, and depending on the color, you can figure out what is done and what is not done. Don't need to go and read through the logs, pipe through data, and all the rest of it. Right, so a test bench that is based on abstraction, and this uses 4 registers for sampling in and sampling out, and builds an end-to-end check for ordering and data loss and all the rest of it that I talked about. So the way we do this is we write an end-to-end check using 2 sampling in registers, which sample in non-deterministic values D1 and D2. And all we are saying is if D1 has gone before D2, then D1 must come out before D2. So this is an abstraction model that I have spoken about in previous talks. So I'm going to use this assertion-based check, and let's see what happens then. Okay, so I run this and I get an exhaustive proof. And as soon as I get the exhaustive proof, I also figure out this is the only check I have, but I've got 63% of the design covered with this one check, and a third of it is unobserved. And it's pretty bad, but I've got about 5% uncovered. So how do we deal with this, and what do we do next? So what we're going to do is we'll click this file here, because this is being tagged as the design file. And now I'm able to see that actually there is a problem in these 2 lines of the design, which is really bad. It seems to think that a lot of logic up here and here is also unobserved. I can't seem to observe anything about empty or full. I can't seem to observe anything around write acknowledge signal. So here I have an exhaustive proof of a design, not a bounded proof, and the tool is telling me there is a problem. So let's debug this. Let's take a look at this closely. One thing that we actually encourage people to think of is if you don't have the appropriate set of checks, it is possible that you're not observing your design signals. So notice that in my ordering check, I haven't got anything about empty and full. So it's quite obvious to think actually I could go and add more checks. So one way of doing this is just go add checks like these. So those of you who are familiar with assertions could say, if I'm empty and if I do a sequence of multiple pushes and no pops, as many times as the depth, then I go full. And I can write the dual for empty. And I need one more check to say what happens to the empty signal coming out of reset. So I'm not saying this is the only way to write it. You can write other assertions that are observing the state of empty and full. So once you do this, the coverage number increases. So now I've got 72% of the design covered. But interestingly, one of my checks have failed. So I can't actually get full to empty to pass. So it looks like there was a bug in the design, which I could not have foreseen before. The tool told me that there was missing coverage. I wrote some extra checks, and now I find a vacuous failure. So let's debug this, okay? So click this hyperlink here, and it will show you this view. Now the two lines that were actually not reachable before, they were marked in red, are now showing as unobserved. And these two lines here, and empty is still unobserved. So let's take a look a little bit deeper. And I noticed that actually in the read acknowledge signal, I've made an error in writing the logic for this. And it says coming out of reset, I'm able to not read the FIFO. So I lower down the read acknowledge. And at all other occasions, other than when I'm full, I have the ability to read it out. So it's actually this corner case scenario when I'm actually full, I made a mistake and ended up writing this line of RTL. So this is preventing the ability to read out of a full FIFO because you can't do a read when it is full. So we can fix it, okay? And the fix is a natural one, so I will fix it and I'll rerun this and I'll show you what the fix is in a second. Now the coverage number has jumped up by 4% more, but now I have no vacuous failures, no other failures. Still the observation coverage is missing. It's now a fifth, incomplete. So let's take a look. And what we did as a fix was to actually say if I'm empty, then don't do a read at all other times, just do the read acknowledge as high. And a lot of handshaking protocols, this is quite normal. I did this, however, still there is a problem, and I still can't actually get the 100% coverage. So what I do now is, at this point, I'm thinking, the tool thinks actually that there is a problem with the write acknowledge. So it's kind of funny because I do have an end-to-end ordering check which does do writes and reads. But the tool seems to think that even though you might be doing writes and read, still the write is unobservable. So what I will do now is I'm going to go and write checks on write acknowledge and read acknowledge. And they're really good checks to write because they can detect deadlocks in your device. So I go and write these checks and I put some fairness constraints to get them to go through. And once I write this, the coverage now is in the region of 90%. Okay? So not only do I get them to pass, I am now only 9% unobserved. And I'm doing really well because I'm still hitting my exhaustive proofs. But what about the remaining 9-10%? Why is it important? So at this point, if I don't have a tool that gives me this information in the form that I have, and if I haven't exercised these buttons, then I'm very tempted to sign off because there is almost nothing that can tell me if anything is broken. The problem is that there is still a bug in this design. And actually, this last 9% or so is actually telling you just that. So let's take a look at this chappy a bit more closely, the very top, right? So I have got explicit checks on the handshake signal. So why does the tool think I'm not observing the write acknowledge? So let's zoom in a bit more and let's take a look at this. What it is saying is coming out of reset, write acknowledge is 1, which is to be expected. The device is ready to read the data in. Should be able to write the data in, sorry. If I'm not full, absolutely fine to write stuff in. But when I do go full, the write acknowledge goes low in the falling clock cycle. So as you can see, there is a potential here that I might be overwriting the data when the FIFO is full. But then why did I not catch this bug? Was my ordering check not good enough, or my other checks not good enough? Actually, as it turns out, we might be having a bug, but we might be having a bug because, and we may not be able to see this because some constraints might be preventing you from visualizing this. So actually, it does turn out at this point that I have a hunch that there is a bug. I don't yet know this, okay? I almost believe there is a bug. So the way to fix this is actually just look at the other places where you might have reasoned about write acknowledge. And actually, given this was a circular buffer, it was reasonable to have a side constraint. And the engineer was given a requirement saying if the FIFO is full, then you either don't do a write, or if you do in the very same clock cycle, you must do a read. Okay? So the problem is when the FIFO is full and you're trying to do this extra write, this constraint takes over and allows a read to happen in the same clock cycle. And when it does it, you're not able to see the effect of this bug, which we suspect right now is a bug. We still don't know. So what we should do at this point is take this constraint away, relax this, and see what happens. And the moment you take this away, the ordering check fails. So you actually had a problem. So it looks like, so our hunch is in the right area. One other check has failed. So let's debug the ordering check. So pull up the wave, and what happens here is that you have a sequence of writes, and the FIFO goes full in this clock cycle. You don't happen to have had any read up until this point. The write pointer has wrapped around, and actually the new value that appeared in this clock cycle, which is 1, overwrites the value at index location 0. And in this abstract model of verifying this through the assertion I showed you, it uses non-deterministic values D1 and D2. So it is quite obvious that actually this D1 was chosen to be 3 and D2 was chosen to be 1. And actually it was expecting to read 3, but it ended up picking up 1 here. So there is a problem. Let's fix it. Okay. So at this point, it is just useful to glance on your dashboard and notice the coverage has dipped from 90% to about 63%, with 2 properties being shown to not have a proof and close to 40% actually unobserved. So let's go fix this. And when we do fix it, we do get a dashboard like this, which is something I was hoping to see just after I had written my very first check, because I thought I'd written a great check. Let's figure out what I did. So I mirrored the logic for write and read in exactly the same way. It's sort of dual of each other. So coming out of reset, if you're not full, you continue to write. If you're full, don't write it. This design now happens to reject any new data when it is full. Okay? So now I've actually built the capabilities in the design itself to reject the data when it's full. That may or may not be the case. You can actually check with your requirements, with your plan, whether you wanted the device to actually have that behavior. In this case, I believe the requirement is acceptable and the designer is happy for you to have that. At this point, I realized that the constraint that I was carrying with me was actually no longer required. In fact, that's now a property of the design. And actually, I should have it on the interface, that when I'm full, I can't write it, and when I'm empty, I can't read it. So now what I've done is I've actually gone in and added 2 more checks on empty and full, and I made sure that the device has that behavior. Then I go back, confirm it with the requirements, and just make sure that this is what it was required. So actually, these chappies here are no longer assumptions on the interface, and in fact, the actual assumption I had written is no longer even a requirement. And in fact, that fails for this design. And the reason it fails is because of the way the write acknowledge signal has been fixed in the design. Of course, if I design it differently to allow the write to happen in the same clock cycle, then the original constraint that could be now in assert would pass. But at this point, this is what the requirements are meant to be. So actually, let's take a step back and see what we've done. So we started off by having no test bench, and we saw everything was uncovered. We then have 1 single check. We got about 60% of the design covered. We then spotted missing checks on empty and full because the coverage browser told you so. We add checks, run the proofs, we find a bug in the design. We fix the design, we run the proofs again, run the quantify, we find more design is still unobserved. So we go write more checks on the write and the read handshakes, and at this point, we expect the design to be reasonably well quantified, but it turns out it was still in the region of 90%. So then we detected that there could be a problem with one of the over constraints, and then it was indeed the case. And when we relaxed it, we found a bug in the design. So what happened here is that all proofs are marked as proven. There were several stages during your development and verification cycle when you had exhaustive proofs. It was not the case that you had bounded proofs. Properties were not marked unreachable. You had passing witnesses. You had checks on all design statements, because I went and wrote these checks I showed you, and yet the coverage was not 100%. And what happened is the tool guided you. Tool is not an oracle. It doesn't tell you what check to write. It guides you into an area of the design and forces you to think. There is a human element involved in this. It would be nice for deep learning to go to a point where we can actually even unearth what would be useful to write. But at this point, we give you hints. And once you do this, you're able to unearth the bugs and the over constraints. So I just wanted to take this opportunity to point out that this stuff works for other designs which are vastly more complex than a FIFO. And one of our lead customers, Infineon, we have an engineer called Holger Busch, who's actually published a paper on using Quantify. And here is some of the data for that. But if you are actually worried about safety, given a lot of the safety work needs to go through compliance and requirements-based verification, this stuff has also been used by Holger at Infineon, and he's kindly published his data where he shows actually how coverage with Quantify would be used for safety. So let me actually just briefly mention this before I wrap up. So there are lots of different coverage solutions in the market, and I can see some people smiling. And to be honest, they're all serving some purpose. The question is whether they are serving the right purpose. So the cone of influence coverage is a great technique to find big gaps quickly, but can lead to false optimism. We have made other presentations where we have showed concrete examples on this. We have the proof core, where the result depends on selected proof engine, and if the more abstraction you do, the better the coverage model, or sorry, the worse the coverage model is, it's more pessimistic. It's hard enough letting designers or verification engineers write assertions, and then you go to them and say, I've got proof cores, I've got this bound, and I ran engine this and engine that, and this is cone of influence. The managers don't get it, right? They don't need more and more complex formal terminologies to get a sense around sign-off. Then there is mutation. So, there are solutions based on mutation, which is a great technique. The only problem is that some of these solutions are implemented around mutating the RTL, which forces people to have too many iterative compile and runs. And some of these mutations can cause vacuity, overall high runtime. So where we believe Quantify brings you is the right level of abstraction where we merge the structural and the functional coverage in one observation coverage model and produce to you a report that is directly linked to the design browser. You show it to a 4-year-old, and even he would make sense out of colors, never mind the experienced managers who have to understand the complexity. So we believe it addresses the problem of coverage in a decent way. And I would strongly encourage the verification engineers to consider doing coverage as part of the design bring-up flow, going all the way to full-on verification. That's where I can wrap up.
Thank you very much. One question online, but we'll take something from the audience first, if there is one from the audience. Okay.
Hi, Wilkin from ARM. It's still possible, even with this solution, though, isn't it, to have 100% coverage and bugs in the design?
It is still possible that you could still have 100% design space coverage, but the technique is actually offering you a way to make sense out of your test bench and the coverage of the whole design. But if you haven't implemented certain features of your requirements in the design in the first place, then there's nothing to cover for. This is where I said the gap free comes in. Because if you have implemented everything in your requirements space into the design, and you didn't have checks, then this method will find it out for you. And it will check which bits of it are unobserved or dead or whatever. But if you actually did not implement features or from requirements point of view in the design in the first place, there's nothing this method can do. For that, you need to use a gap free, where we actually just take the specifications themselves and run the whole analysis for completeness. That's a separate talk. I can talk to you about this if you like.
Okay, but you could go through the same iterative process that you showed on your design with proof core, for example, and achieve the same result. So I'm struggling to see the
possibly
advantage.
But so not too long ago, I was able to use some of the tools because of my association in the verification world. I didn't see that, but I guess the people who are building these solutions could. I mean, I've looked at examples like this and run those tools, and I haven't seen those problems appear. And it is possible that the proof core or the mutation or the cone of influence or all of them can find this too. But can they express it in the form that makes it easier for you to look at and communicate with your managers? And that's the main aspect. I mean, it's not like the other solutions are bad, right? It's just, as I said, whether they're quick and easy and whether they allow you to have it in meaningful format. And yes, as I said, this is not a validation. It is not addressing a validation problem. It's still a verification problem. But it is true, yeah, the proof core could potentially find it. Actually, we do have an example where if we do a proof core based analysis, especially cone of influence in particular, is very dodgy. Because if you end up writing an assertion which actually says, I can see the data being written in is read out, but additionally the FIFO could be full or empty, then the cone of influence, because the full and empty flags will cover the whole of the design, the cone of influence would actually say, you've got 95% coverage. And your actual property would be saying, I've just written one piece of data and just read this one out. So there are technical reasons why cone of influence is not the best technique, but I could point you to a presentation where we have explained this in more detail.
Okay, yeah, interesting. Thanks.
Thanks, Phil. There's a couple of questions online. Ashish, should probably worth asking, please. The examples are all from bounded full proofs. What about bounded proofs? Can we extract useful cone of influence and coverage information from bounded proofs and apply it?
And the answer is yes. There's a switch called use bounded results. And you run this example with use bounded results and you will get exactly the same story.
And second question is, what about merging the Quantify metrics with simulation coverage? Everyone's been working on that. Is XIII UCIS discussing it?
Yeah, so that's a good question. So we have been looking to merge the runs of Onespin formal with simulator results. And we have done successful integration with Mentor's Questa and Synopsys' VCS. We have not looked at integrating Quantify yet, but it all depends on where is the need. So right now we have 1 or 2 customers who are actually using simulators and they're using our formal runs and they're able to take the results of assertion runs and integrate this back into their verification planners. So the solution that we've prepared is more on verification planning and tracking, because we want the end customer to have the same view of simulation and formal in the same verification plan that they have, not having to have separate views and so on and so forth. So we've just done this recently, and we're working with some lead customers to deploy this. Okay. We've already done 1 deployment so far.
And one final request to share the pointers to presentations where COI is not the best solution. So.
Okay, yeah, so we can do that. So I think those presentations have been done in the past. We could provide more information. If you send them to Sarah, then share them to the audience. Yeah, okay. Let's do this the other way. Let the person get in touch with us and do.
Should just proofread them before she sends them out.
No worries. Yeah, we're happy to do that. Yeah.
Okay, that's it. So thank you very much. Thank you very much.